We stand on the shoulders of giants. It's weird. It's like this technology we inherited from a previous civilization. It's like, what are all these nuclear power plants? We kind of stumbled upon them. Data centers used to be, a big data center used to be 10 or 50 megawatts. Now they're multiple gigawatts. We have sucked up all of the spare capacity and optionality in the grid. The hyperscalers need to step up and make longer term investments. Every nuclear plant that's ever been built has been backstopped by taxpayers or ratepayers in some way, shape, or form. Because the cost overrun and the schedule overrun risk is so high, nobody but the government is willing to take the risk and backstop the risk. We, through this method of fabrication, we at Blue Energy think there is a way.
Welcome back to the Interchange Recharged. Today we're talking about nuclear power, energy generation that's been commercially available since the 1950s, yet we've hardly built any new capacity in the US over the past couple of decades, and the one major project that we did complete cost more than twice what was originally anticipated. But we see that AI and data center demand is really breathing new life into nuclear and is viewed by hyperscalers as a highly coveted, low-carbon source of baseload power. And over the past year or so, we've seen Microsoft announce that we'll restart 3 Mile Island. Meta has signed deals for 6.6 gigawatts of new build nuclear power, and there's a lot of interest. So today we're talking about why it's been so hard to build nuclear in the past and what is changing today in order for nuclear projects to become financeable, repeatable, and scalable. And to facilitate this discussion, I'm joined by Jake Jurwitz, founder and the CEO of Blue Energy. Jake, welcome to the show.
Thank you, Bridget. Happy to be on.
Now, Jake, I hear that you're a nuclear history buff, and before we get into your company, I was hoping that you could help give us some background on the topic today. And we've got about 93 or so operating reactors in the US, the latest one being Vogtle. But when was the last time that the US had built a new reactor before the Vogtle facility?
Yeah, before Vogtle, I think to kind of complete the story, there was another set of AP1000s that were being built at the same time as Vogtle, which were the VC Summer units, which never got completed. And there are conversations now going on about restarting that construction process. Before that, the last one that got completed was Watts Bar 2, if I'm remembering correctly, which was also another nuclear plant that had been mothballed. It was partially built and then mothballed for multiple decades and then finally completed. I think it was in TVA's territory. Before that, you have to reach back pretty far where you had like a traditional, new build to completion nuclear plant. I might be misremembering it, but it might have been Palo Verde in Arizona. Might have been the most recent one before that, but frankly, it was quite a while ago. So it is not unfortunately, it's not a muscle that the U.S. has really built within our construction and supply chain organizations.
Yeah, and I think the U.S., we built a bunch in the 60s, 70s, and 80s, and like you said, you have to reach quite a far ways back in order to see when we last built them. But I mean, why did we stop? Did other countries stop as well?
Yeah, so roughly the build out happened shortly after the Manhattan Project. There was all this interest of nuclear technology, and we saw the light water reactor technology we have today that represents most of the nuclear power plants around the world was originally invented by the U.S. Navy to power nuclear submarines. That was the first pressurized water reactor. And then the utilities brought that on shore and scaled that up to make the first commercial nuclear power plant, which was the Shippyport nuclear plant in Pennsylvania. And that was in, I believe, the 50s. And then you saw a build out where we kind of kept scaling up that baseline PWR technology. And then GE introduced the boiling water reactor after a couple of experiments in Idaho National Labs called the Borax experiments. So then you saw these two flavors of reactor technologies, pressurized water reactors and boiling water reactors, that just kept increasing in size as we built units mostly in the 60s, the 70s. And then something happened in the 70s, which was, yes, the energy crisis happened in the early 70s, but then the entire period of basically 1970 to the early 1980s was a period of significant stagflation. Inflation rates were very high. Therefore, interest rates got very high for borrowing capital. And because of a lot of the energy efficiency programs that had started to be imposed from the energy crisis in the early 70s, utilities started to see a drop or really a flattening in load growth. So all these projections for what they thought were going to be new power plants, which included a lot of nuclear plants, they started canceling a bunch of them. So you saw a large number of nuclear project cancellations because simply the load didn't show up for the utilities. And that was compounded by the effects of that 3 Mile Island had, and then eventually Chernobyl in the early 1980s that restructured the entire way we do nuclear regulations in the U.S. We split up the Atomic Energy Commission into what is today the U.S. Department of Energy and the Nuclear Regulatory Commission. So we separated those two functions within our government. And we haven't really seen a big build program since then. That was when we were building nuclear plants at the fastest rate. It was, I believe, the 1960s. And you saw a few new ones get built in the late 80s and 90s. And then it really has stalled since then. Again, partly because we haven't seen load growth for the last 25 years.
But here we are.
And now, which has changed dramatically in the last 3 years.
So I guess before we go into the AI and data center demand, I want to bring up the example of Vogtle, which is the latest facility that's been brought on, at least in the U.S. market. It was supposed to cost $14 billion. It ended up being twice as much as that, from what I can see on the internet, between 34, 35, 36 billion. Nonetheless, we're in agreement. It's more than double, and construction took about 12 years. What went wrong with that facility? Why did it cost twice as much and take so long?
Yeah. So when you look at the data on why, where is the cost overrun happening in nuclear? It's not unique to Vogtle. The same issues have plagued Europe with the Hinkley Point C project that's ongoing in the UK, the Flamanville project in France, Olkiluoto in Finland. And the reason for that is the nuclear equipment costs, what you would think would be the expensive part, like what makes a nuclear plant, the reactor pressure vessel, the heat exchangers, the steam generator, the isolation condensers. That equipment actually represents a very small sliver of the project costs, like on the order of 7%. Most of the cost in nuclear that has caused the cost overruns is what I call nuclear construction overhead, or what is sometimes called the indirect EPC fees. Owner's costs also get baked in there. And this is really the cost of training and relocating the 10,000 or so skilled workers to a site like Vogtle that it takes to build these nuclear plants the traditional way, right? These plants are essentially designed as large-scale civil infrastructure projects similar to building an international airport like the Denver airport, which also was plagued by cost overruns and schedule overruns. So it's also not a problem that's been unique to nuclear. It's more of a problem that tends to stem from doing large-scale infrastructure projects in the West, where we have a lot of stakeholders. We have a highly distributed governance system. There's local, state, and federal level permits. There's lots of interveners who can get involved. Mm-hmm. And when you have to mobilize 10,000 workers, which in the context of nuclear construction means you have to train them to be nuclear qualified steel workers, welders, concrete workers. They're doing paperwork and procedures that they have likely never done before in their entire lives. So you're training them. You then have to retain them because once they are trained, they're a pretty hot commodity. And especially in the days of building data centers today, they can easily get poached by another construction project somewhere else. So you're often paying to retain them. And you have to set up nuclear quality assurance programs in the field. And anybody who's worked in a factory or, as we'll get to, shipyards and fab yards versus in the field construction, they'll always tell you things are more expensive in the field. They take longer than you expect in the field. Sometimes it's simple things like weather that you can't predict, hail, storms, knocking things down, reducing productivity rate. But oftentimes it's just the unfamiliarity that craft labor has, that any worker would have navigating a real world site in the field, getting their stuff, where are their tools? What's the procedure? How long does it take to walk to the job site? Do they have to climb up or down some temporary set of scaffolding? And, if you go into a unionized labor state, how many people need to be involved for oversight and change of shifts? How long does the change of shift take? There's all this, what I kind of call, there's a lot of surface area for critical path expansion for things to go wrong. And when they do, it causes cascading delays because
that gets reflected in the cost.
And it all manifests in the cost. And then it gets compounded further by, if this is being debt financed, the interest rates just compounds. The longer the delay is, it costs more.
The longer the construction is, yeah.
Yep. The longer the construction is, the more it costs to reschedule that concrete truck or that, pipe layer or pipe fitter, and everything just costs compound. And it's very easy to happen in the field, especially when it's a complex logistics exercise with many different forms of craft labor coming into the site. So
that equipment cost, you said the reactor equipment cost itself is 7% of the total cost typically, meaning that 93% comes from construction, cost overrun, interest. Is that right? Yeah. Roughly a third of it is the capitalized interest on debt, and on the order of 40%, 45% can be the construction overhead for the project. There is, of course, the other materials and equipment for the actual balance of plant, steel and concrete that make up the plant. But the vast majority of it ends up being this indirect EPC costs. Okay. And you also said, if I can summarize, that this is not atypical for nuclear construction or really any kind of construction, but this type of insane cost overrun of being more than double, 2.5 times for Vogtle is not one-off. It is typical. Is that right? Well, it's certainly something that gets observed in other large civil infrastructure projects like big international airports or big tunnels or bridge projects. But I will say, in the context of power plants, the capitalized interest on debt and these indirect EPC fees are, as a percentage and as a proportion of dollars per kilowatt of CapEx, they are much higher in nuclear than they are in wind, solar, natural gas, or pretty much any other kind of power plant construction that you would see. And that is, so you do have to kind of ask your question, like, why is nuclear penalized in this way? Why can't we build a nuclear plant the way that we build other forms of power generation? And I think it's a worthwhile question to ask. It was sort of a question I asked myself when I was sitting at Exelon. And you kind of go, oh, all right, what of all the types of power generation we have been building for the last 20 years, what do they all have in common? We're building a lot of wind, solar, and combined cycle and simple cycle natural gas plants. If you look at all those power plants, pretty much all of them, the vast majority of the equipment is fabricated in a factory, transported to a site, and bolted to the ground. Wind and solar builds are more crane logistics than they are on-site fabrication. For simple cycle gas turbines, it's mostly logistics of transporting and bolting things to the ground. Combined cycle has some on-site fabrication, but if you pick the site right, we've actually prefabricated and barged in entire heat recovery steam generators and a lot of the stuff that you might fabricate on site for a combined cycle plant. So it's because we build them frequently. It's because we build them differently. We build everything we can offsite. All the complexity is done offsite. In many cases, it's done in an automated, robotically kind of controlled environment, particularly in the case of photovoltaics and batteries. In nuclear, we have really not even scratched the surface of what could be automated and prefabricated offsite. It's very old school. Part of shipping all of the workers to the site. It is very, it's like how we built a castle like 700 years ago. It's a lot of shipping raw materials to the site, mobilizing effectively a small town of people to erect these things. And we shouldn't be surprised. That is not very efficient, especially when they're out of practice. So really the opportunity is tremendous. There's a lot of potential for stripping costs out of nuclear builds. And I think rather than criticizing nuclear, when you start to uncover
the root cause as to why it's as expensive as it is, you start to realize, oh wow, there's actually there's a lot of cost we can strip out of this.
So tell me about blue energy then. What is it that you guys are doing to tackle this cost of construction? Is that where your focus is?
Yeah, well, when you kind of approach it that way, you go, okay, how are we going to bring the cost of nuclear down from the $15,000 per kilowatt that we're experiencing today closer to, sub 5,000, maybe even closer to $3,000 a kilowatt, which is close to what we're building a combined cycle at today, and close to what we're seeing nuclear get built in South Korea and China today. So, like at a base level, you go, actually, that's a reasonable goal. That people are achieving that today in parts of the world. So why shouldn't we be able to do that here in the US and Europe? And we approach it at Blue Energy and say, where can we take the lessons learned from what has worked well in adjacent energy sectors? Where have we built big pieces of energy infrastructure on time and on budget well enough such that they could be project financed the way that we project finance wind, solar, and gas? And that is to say, such that we could debt finance them without a lot of or any government intervention. You could privately finance new builds of nuclear plants. And we've been inspired by what we've seen work in the offshore sector, specifically LNG, offshore oil and gas, and offshore wind, where pretty much everything is prefabricated out of necessity. Everything is prefabricated at these fab yards and shipyards around the world. And they really are around the world. You can see competitive prices for these projects get bid out in South Korea and Southeast Asia and Northern Europe and in South Texas, where we can prefab everything in these existing oil and gas fab yards and then barge it to the operating sites. So rather than limit ourselves to what could fit on the back of a truck, we say, let's intentionally pick sites where we could barge in very large, fully outfitted, on the order of 2,000 tons or more modules that are basically fully functional subsystems that in some cases can be even tested and commissioned in the fab yard rather than on site. So you really shrink the scope of what is done at the operating site and move as much as you can offsite.
Let's unpack this because there's a lot that you've just mentioned. So prefabrication, meaning that you're building components in a factory or in a fab yard and then transporting them to the fab yard for assembly. How does this work for nuclear? I mean, maybe break it down for me in a really simplistic way. Nuclear facilities are big.
Yes.
How are you prefabricating this equipment?
That's right. So you can I think of the nuclear market in sort of three categories. For the last several decades, we've just been scaling up reactors to bigger and bigger sizes. And that has forced us to do most of the fabrication on site because they have gotten so large. And these are like the EPRs, the ESBWR, even the AP1000. They're 1,000 megawatts plus. And those functional subsystems, the containment system, is so big, you really do have to fabricate it on site because it can weigh on the order of 100,000 tons. It's mostly a giant reinforced concrete block with a lot of heat exchanger equipment baked into it. That equipment. So what we're doing, I guess that's one category of how we've built nuclear, and it does force you to do things on site. The other extreme is the microreactor environment, which we're starting to see new microreactors come out, which are mostly Gen 4 reactor technologies that take on a lot of technology risk. What we're doing is in between. We're focused on this new category of light water, small modular reactors for the beginning of what we want to do. And the reason we're starting there is it's already mature technology. It's essentially just a shrunken down version of what we've been building and operating for the last 70 years. The reactor equipment itself is already coming from the factory. So the reactor pressure vessels are already built in factories. They're built at forges. The expensive part of a nuclear plant is all the structural steel and concrete that goes around that reactor pressure vessel. So it's the nuclear, sometimes called the nuclear island. It's where the containment resides. But it's all these nuclear safety systems. It's a lot of auxiliary systems. It's refueling equipment. And for the large reactors, that is just too big to plausibly transport, at least to most sites, and to prefabricate that and plausibly transport it, because it's just too large. It would be impractical or too expensive to move it on a barge. But these light water SMRs are small enough where you could actually just borrow some of these form factors and transportation techniques from the offshore oil and gas sector, which regularly transports 2,000 to 10,000 ton modules for offshore oil and gas projects. And we can reach most operating sites that you might want to build a nuclear plant anyways.
So a small modular reactor, it is small. How small is small? Like a house?
It is bigger than a house. It is much smaller than the gigawatt-sized nuclear reactors that we've been building and operating for the last several decades. The small modular reactor category kind of ranges in size from about 50 megawatts up to 300 megawatts, roughly, in size, in terms of megawatt output. In terms of like physical proportions, this is probably half a football field, roughly, in terms of area that it's taking up.
I can see why road transport or trains wouldn't work, and you're kind of required to use barges in this sense as well. But you said that when you're choosing sites that can purposefully have the equipment delivered by barge. Who is it that Blue Energy is working with? Are you working with reactor developers? Are you working with hyperscalers or utilities?
All the above. So we're a technology-enabled developer. What that means is we act as the developer. We go out and find the land, and we carry out the permits, interconnection, design, engineering work, stakeholder engagement to pull the financing together. But I say we're technology-enabled because we do take a proprietary approach to how we pick the sites, how we do the detailed design on the plant, how we do the logistics and the execution such that we can prefabricate it and barge it in this way. And the reason that's so important is that we can leverage, when you go to the fab yards and the shipyards, you can actually go and get fixed price contracts, whereas you can't get that from a traditional EPC to have it fabricated on site. And the reason you can't get a fixed price contract from a traditional EPC on site is, one, they don't have the experience, so they don't have the comfort in taking the risk on giving you a fixed price. But two, they're not willing to wrap the risk on procuring and retaining the labor, because there isn't a large supply of nuclear qualified labor out there that they can just tap into the way that they can. It's even hard to find craft labor for non-nuclear construction projects. But when you go to a fab yard and a shipyard, they already have several thousand craft labor on site. Some of them are already qualified to do nuclear fabrication. They have an existing installed base of fabrication equipment. They're constantly buying steel. They have a roof over their heads at minimum, which does a lot for your productivity. And some of them even have started to make investments in automated robotic welding and quality assurance programs. And they look much more like an automotive factory, mass production line. Those facilities then are able to guarantee labor and labor productivity in such a way that they can give a fixed price contract. And that's a big deal, because if you can get a fixed price contract on big blocks of the plant, then you can go to the banks and say, hey, instead of building this nuclear plant out of 100,000 Lego pieces and just paying somebody a cost plus contract to assemble those thousands of Lego pieces, who knows what it'll cost and who knows how long it'll take. I can now make my nuclear plant out of 5 or 6 really large Lego pieces. Each one has a fixed price contract, and each contract marries up in such a way that there's very little daylight between them. And the banks are actually familiar with that. That is how offshore wind contracting worked. That is how some LNG projects were contracted and financed. And they can actually loan against that. And that dramatically reduces the cost of capital and the risk of the project.
Well, I think fixed price contracts, those work so well because the contractor commits to a price and then agrees to absorb any overruns. And it sounds like nuclear that historically is quite common. But before we talk more about financing, I just want to really wrap up the picture for the audience about who Blue Energy is. You're working with light water, small modular reactors. You're working with anybody from developer, hyperscalers, utilities, etc. But when you said, there's a lot of prefab yards that have these existing capabilities or are working on capabilities or have this craft labor, does that mean that you're looking to, lease out a fab yard to build a SMR for a project that you're looking to deploy to? Or does that mean you have your own fabrication facility? Do you have any projects right now that you could use as an example to kind of solidify what your role is in the supply chain here?
Yep. Yeah. So like I said, we're playing the role of the developer. So we are engaged with light water reactor OEMs as technology providers. We're engaged with hyperscalers as off-takers. We're engaged with EPCs, fab yards, and shipyards as part of the supply chain to enable this means of project financing nuclear for the first time. So we are not ourselves building out a factory or building out a new shipyard or a fab yard, but we are contracting the existing oil and gas fab yards and shipyards to basically tool themselves in such a way that they can fabricate these large modules for building new nuclear power stations. We may in the future get into some fabrication ourselves, but this is, we think, is part of our strategy is we don't have to wait or take on the additional financing load of building a new factory. We can use the existing fab yards and shipyards around the world and use that allows us to scale this very quickly.
And it sounds like Blue Energy, based on the structure, you basically have unlocked the ability to do project financing for nuclear, which, as you said, hasn't really been done before. It sounds pretty straightforward the way you've laid it out, Jake. Has modular nuclear construction ever been tried before?
Yeah, well, I'll put it this way. The nuclear industry has been talking about and using the marketing term modular construction for a very long time. And it's even seen some success in building, I think the world record for building a new nuclear plant was set in Japan. There was an ABWR that was built, I think, in about 3.5 years. We've never really been able to replicate that in the US and Europe. And it sounds straightforward, but it's a very unique and I think a pretty powerful statement to make that I don't actually think the energy markets have fully internalized what this would mean. Is what we're planning to do at Blue Energy is present the world's first project financeable turnkey nuclear power solution. That would mean it is the first firm capacity, fuel secure, zero carbon, dispatchable generation asset that could ostensibly be located anywhere because it doesn't need a carbon sequestration sink. It doesn't need a geothermal vent as input. It just needs a place where we can get it permitted, which are a lot of locations around the world. So that would fundamentally change, I think, a lot of energy markets to be able to debt finance a nuclear plant without government intervention. Every nuclear plant that's ever been built has been backstopped by taxpayers or ratepayers in some way, shape, or form. Because the cost overrun and the schedule overrun risk is so high, nobody but the government is willing to take the risk and backstop the risk. We, through this method of fabrication, we at Blue Energy think there is a way where we can borrow the best practices and the supply chain, the form factors, the contracting protocols from offshore oil and gas, from offshore wind, from LNG, and apply it using the new light water small modular reactor technology for the first time to enable project financing for nuclear for the first time. It fundamentally does change the way you build the plant. It changes the way you design the plant in some sense for this kind of construction execution. But it's already a de-risk technology. The fuel supply chain exists. We know it can operate at a high capacity factor. We know what the operations and maintenance costs are. So you have everything you need to be able to debt finance it, except for how much is it going to cost to build? How long is it going to take to build? That is the sole problem that Blue Energy is focused on. Okay,
so you're looking to establish those cost figures such that it can be turnkey. What's the downside? What's hard about what it is that you guys are doing? Is it the coordination side of things? Is it, transport logistics or just coordination logistics overall, upfront capital? What's hard about it?
Yeah, there's what we're doing in order to enable it to be project financed, it means we've got to work with mature reactor vendors, at least to start. And that means a lot of coordination with a lot of major, large stakeholders, companies that have a lot of inertia, but also some suppliers who are still retooling and getting comfortable with the build out of nuclear that this administration is planning for. So it's a lot of coordination, but it sounds simple to say, all we have to do is just build a nuclear plant on time and on budget. That is something that no one's really been successful at achieving. So we want to make sure that we are not making the mistakes of the past. We want to learn from all the nuclear projects that have been done before. We want to learn from successful oil and gas, CCGT, LNG, offshore wind projects on how we can translate what has worked in those projects to the nuclear sector. It's a challenge. It is also a challenge for raising capital because we're a weird kind of company. Normally, when you go out and you raise venture capital, you do so on the back of, we're going to invent a wholly new widget. We own this new widget. No one else can make this new widget. And we'll therefore have a monopoly on this new widget. And venture capitalists will invest in that. And usually you can start very small. Like your minimum viable product maybe only requires a few tens, maybe a few hundreds of millions to build. Mm-hmm. In our case, we've got to jump to some means of project financing right away to get what is at least $1 billion or $2 billion of capex financed for the first unit. So we've been engaged really early on with banks and project financing and infrastructure funds. We have raised a significant amount of venture capital to do this. But there is sort of this funny world we live in between venture capital and infrastructure funds, which are two very different risk profiles and types of investors. There's a lot of investors, I think, swirling around the hoop right now on wanting to invest in nuclear. And Blue Energy is at the intersection of all of that. It also means that we're not doing permissionless innovation. A lot of the innovation that we're doing at Blue Energy requires the permission of some of these large stakeholders. That is different than what you're seeing some of the microreactors do right now, where they're designing a new widget. It's probably the smallest, most minimum viable widget they could think of in the context of nuclear power. And to some extent, they're kind of operating in the belief that they don't need anyone's permission. They can go and pursue permissionless innovation, which is a very kind of traditional Silicon Valley approach to doing these sorts of things. I think in the context of nuclear, you can't get away from needing permission. You need the Nuclear Regulatory Commission to be bought into it. You need your neighbors and state representatives and local representatives to be bought into it because you are putting fissile material in a semi-permanent location and creating radionuclides. So you've got to be thoughtful about nuclear safety and security. We're able to piggyback on a lot of that. We have a lot of experts in our company that have been attracted to this approach because we think we have a respect for the history and the complexity of what it takes to get a nuclear project done. So we're very intentionally not taking risks wherever we can, and so that we can just focus on the risk that matters most, cost and schedule.
Right.
That being said, I'll add one more thing, which is that because this is important for raising capital, that doesn't mean we don't have an opportunity to create a sort of a monopoly-like business, at least in the beginning, because whoever is able to show the world that you can project finance a nuclear plant, it's going to be very hard for others to replicate that. Customers of nuclear are very risk averse. They want to buy a nuclear plant from somebody who has built it on time and on budget before and has the lowest cost of capital, has the supply chain and the regulatory and relationships to pull that off. I don't think that's a trivial thing to replicate, certainly when there's intellectual property, know-how, and regulatory approvals involved.
So tell me about a lot of the things that you mentioned make me think of you guys are really a first mover in the space, maybe a first mover for light water SMRs. Maybe you can tell me if there's any operational. You're basically trying to create like a cookie cutter template here that's, like you said, turnkey, financeable, replicable, financeable, as I said. But the idea is to deploy quite a number of these. So tell me where you're at. How many projects do you have on the backlog? Are you getting bites from hyperscalers per se? Are they helping accelerate the market?
Yes, I think it's it's an important nuclear power is an important asset for the whole global energy system. But the demand that we're seeing right now from hyperscalers is an excellent beachhead market to help pull that future forward, because they have the existential need for the power. Not just because some of them have carbon goals that they want to hit in a decade or two, but because nuclear represents a fuel diversity play for them. There's a lot of, I would say, over-reliance potentially on gas infrastructure in the long run, and we're seeing there's can be a lot of volatility in global gas markets as we're seeing right now with the Strait of Hormuz being closed. So where we're at today, we've announced our first project publicly, which is the Port of Victoria in Texas, where we're working on the development of a 1.5 gigawatt nuclear-powered co-located AI data center in partnership with Crusoe. We've been engaged with the community there for a long time. There's still a lot of work that has to be done on that site to progress it through all the approvals and the financings, but we feel really good about that site and the potential that it has. Like I said, that's a 1.5 gigawatt build out. We're also doing something else unique at that site to de-risk it, which is that we are doing the world's first gas to nuclear conversion. So we're actually going to be building, this is a way of helping to de-risk and help capitalize and finance and enable project financing, even on the first unit, without the need for government support. And that is that we're building the balance of plant for the nuclear unit first. We're building that steam turbine system, condenser, interconnection, cooling towers. And then we're firing it early with 2 combustion turbines as a 2-on-1 combined cycle plant. And then we are building the reactor and splicing in the nuclear steam and switching it from steam coming from the heat recovery steam generators from the gas turbines to steam coming from the nuclear reactor. And then we are opening up the bypass on those heat recovery steam generators, and we're switching those gas turbines to simple cycle mode to serve as essentially peaker capacity and backup power to some extent for that co-located data center. So it's a broader project that allows us to accelerate our commercial operation date. It also allows us to reduce our cost of capital for half the capex for that first small modular reactor. Even if we don't get any support from the federal or the state government for loan support or other forms of financial support. So we think there's a way to do this, truly even with private finance on the first unit. Then we'll be building out additional nuclear units on that site, as I said, to get up to that 1.5 gigawatts. We've got a pipeline of a whole bunch of other sites around ERCOT, PJM, MISO, New York. We're starting to look at sites in Europe and even Southeast Asia in the early stages of development. There's a lot of different utilities and IPPs and hyperscalers that we're engaged with on all of those sites, but we can't make any of those public quite yet.
Sure. Yeah. Well, thanks for sharing what you have in the pipeline so far. That combined cycle nuclear playing quite nicely together to help accelerate your schedule and even keep the budget low. That's quite an interesting collaboration that I hadn't really heard of or heard of before in the market. Is that something that you anticipate? I think it's obvious that hyperscalers have a desire for speed to power, have a conscientiousness for low carbon power generation that maybe nuclear can help out with here. Do you expect to participate in more of these gas turbine nuclear combined projects?
Yeah, so we originally conceived of it as a way of accelerating and reducing risk on the first project as sort of a catalyst for getting small modular nuclear into a project financeable space. And as we started to develop it, we then realized there seems to be a lot of appetite for it in certain jurisdictions that are looking to build gas near term, but need a pathway to potentially decarbonize it longer term because for whatever reason, post-combustion carbon capture doesn't pencil there, hydrogen blending doesn't pencil there. They maybe have a desire. You can think of certain countries that have a near-term need to even decarbonize a little bit. I can think of like Poland, for instance, where they're heavy on coal right now. where a combined cycle would dramatically cut their emissions. And they want to invest in nuclear, but maybe they don't have the infrastructure set up yet to go straight to nuclear. And I think there's other parts of the world like this as well, where they don't yet have the nuclear regulatory or liability or insurance framework in place. This serves as a stepping stone for them to get there, where we can get them on a very dense, very efficient power generator with gas in the near term and truly use it as a shared facilities and dual use it for nuclear in the long term. So yes, we are actually seeing more appetite for it in the market than we expected. And we've recently gotten the NRC approval on a topical report for this through a methodology whereby we can actually build, we call it balance of plant resequencing. We can build the balance of plant first, fire it with gas, do so without an NRC construction permit, and then switch it to nuclear steam later, going through the nuclear licensing process. And there's a lot of intricacies on how we do that, both technically and from a permitting standpoint, to make sure that we can use that steam turbine in both contexts. But that has recently been approved, and we're excited about what that means for deploying this in a lot of other power markets, and potentially in New England, in northern states, in parts of the world that have a really near-term need for generation capacity and a long-term desire to diversify their fuel mix.
Right. So maybe we can talk about, we've spoken about how hyperscalers a little bit are providing some demand certainty, how their requests for flexibility of power generation are creating interesting developments for nuclear's compatibility with other technologies. But what about the announcements that we've seen over the past, year or two? For example, Microsoft is restarting 3 Mile Island. That is a restart. That's not new construction. And so maybe the real test will be like Meta's TerraPower and Google's Kairos deal, which are actual new builds of technologies. And these are targeting delivery in 2030, 2035. Are those timelines realistic? What timelines are you targeting?
Yeah, so I think the restarts, the uprates and the restarts make sense. They're the lowest hanging fruit if you're trying to get new nuclear capacity. Unfortunately, there's only so much low hanging fruit to pick. We only have so many existing reactors, and we've already uprated them quite a bit over the years. And there really are only a few nuclear sites. You've mentioned 3 Mile Island. There's Palisades in Michigan. And I think Duane Arnold now has been announced as well for restart. Beyond that, it gets very difficult to restart a nuclear plant that's been shut down longer because it starts to get to a cost point where you might just build a new nuclear unit. The announcements you mentioned that Meta made, a lot of that is related to uprates and existing capacity, and then there's also some elements in there with TerraPower and Oklo on new build. I think for 2035, it's about 9 years out. Well, we'll call it roughly a decade out. I think for advanced reactors, which I'm very excited about those technologies maturing, there's still a lot of technology, supply chain, and operational risks that need to be put to bed on those. I think it's very feasible to have some of those first units operating by 2035. I don't know if they'll be operating at a high enough capacity factor where you could make them bankable and truly project financeable, the way that we need power plants to be. But I think what's the saying goes is like we always overestimate what we can do in 2 years and underestimate what we can do in 10. I think that's often why you see some of these more audacious technologies say we'll do it in 10 years. It's like I believe it's if we really organize, we can get it done. But don't underestimate the risks that are still in front of us. And wholesale power is a very risk-averse market. Mm-hmm. I think what we have at Bull Energy is a faster path to get those new nuclear units online. I think we can beat 2035 by years and get to COD on a gigawatt plus site, even a gigawatt and a half, as we're planning for our first site, well before 2035. And I think we can do it and show the world that not only have we done it, but we can project finance it and we can repeat it. And we can then debt finance this and keep scaling it up for other sites.
So then how is it that your projects, which if they're turnkey, I can understand how they're going to be more financeable and more bankable than perhaps a advanced nuclear project that you might be competing with. But then maybe tell me what makes a nuclear project bankable? What makes like the advantage that you have over your competitors is that you're turnkey, but you can move more quickly. You can take on the risk.
Yeah. So what makes a nuclear plant bankable is what makes any power plant bankable. It's a very high mark to hit with the banking community. It basically means you need to be able to project your revenues and your expenses to a sufficient degree of certainty and have contractual protections in place for pretty much every risk that could befall the project. So it means you need to know your capacity factor. It means you need to know your fuel cost. You need to know your operations and maintenance costs. You need to know your revenue, which means you need to have a long-term power purchase agreement at a sufficiently high price to justify whatever the term on the debt is. It means you need to have contracts in place on the cost and the schedule on all the elements of the build, such with enough, backed by not just fixed price, but fixed price backed by companies with large enough balance sheets standing behind it with liquidated damages that the banks will say, when you say fixed price, like you and what army, and a startup's competitive advantage is not its balance sheet. So it's not us giving the fixed price guarantees. It is these fab yards, these shipyards, these OEMs that we're working with who can actually stand behind them. It means you need performance guarantees. And again, you need performance guarantees backed by a company with a balance sheet that can actually provide those performance guarantees. That's another area where I think it's just challenging for some of the Gen 4 reactors to do that without someone with an enormous pot of gold to stand behind it and say, yes, I will guarantee this. And then it means you need to have all the permits you need, not just the nuclear permits, but the interconnection and everything you would need to actually carry out and execute the build. There's a lot of pieces to it. It's why we built the team that we have with experience doing project finance in gas and in wind and in oil and gas projects. And we see a path to doing it based on the strategy that Blue Energy is pursuing, using mature light water, small modular reactor technology, using the oil and gas fab yards and shipyards that have done this type of multi-contracting approach in the offshore energy infrastructure context. And then it comes down to building the coalition of partnerships and executing on it.
From what you've shared, and we've spoken about a lot of different topics within Blue Energy today, but from what you've shared, it seems like a very promising way to be able to deploy more nuclear in the future. And I guess I would ask you, as we're wrapping up, for listeners that are tracking this kind of nuclear renaissance that we've seen and that we hope to see over the next couple of years, what is it that we should be watching for? What signals whether this is real versus it's just more announcements? You mentioned long-term PPAs.
Yeah, I'll always be careful. I'll never say anything negative about other nuclear companies because I'm a nuclear power evangelist. I'm excited about all the different nuclear power opportunities that are emerging with this nuclear renaissance. But in order to kind of separate the signal from the noise, yes, you want to see binding PPAs with creditworthy counterparties, entities that are AAA rated, or so anything that's investment grade, double B plus. Obviously, the hyperscalers are kind of AA, AAA rated. So those binding PPAs are important to see. I think following the larger scale kind of wholesale power, like what is a commercial power project, not a prototype, not a research reactor. While those are exciting, they don't move the needle in terms of putting a dent in our power needs. So it means you got to ultimately go through the Nuclear Regulatory Commission process. You've got to pick sites and pick utility partners and pick hyperscalers and fab yards, EPCs, and OEMs that can stand behind this and scale it up. So those are those are the things that I look for are the companies with the big balance sheets putting their names behind this, both for offtake and for build and execution. Everything else is exciting and it helps move the industry forward, but it isn't putting a dent in the power problem that we need to address right now.
Right. And I guess, as a nuclear evangelist, if you could put a dent in something, could change one thing, like one policy, a market structure, a financing mechanism, what do you think would make the biggest difference for scaling nuclear of any kind?
I think we actually have the policy environment we need right now and the regulatory environment we need. Regulatory is important because you need to strike a balance of being focused on actually building things, but also being really focused on ensuring safety for the public. And I think some of the new commission that's materialized in this administration strikes that balance. I think this administration has been putting policies in place that are throwing the support of every part of the executive branch behind nuclear. And it's one of the few topics that has bipartisan support in Congress as well. So I'm optimistic about the durability of the support for nuclear for many years to come. So I actually don't think that is what is missing. I think I want to see now the capital markets respond. And I think it's about showing them the path to getting this deployed and unlocking that 300 plus billion in dry powder that infrastructure funds have right now to deploy, showing them that there is a path to deploy that capital into nuclear power. That I think is the next step. And I would say also, I want to see the hyperscalers sign the PPAs that'll move the needle, not just do small scale pilots to check a box for some internal feel good obligatory reason. I want to see this be part of the strategic case for the hyperscalers. I think for the hyperscalers, energy has become much more existential to them. A big data center used to be 10 or 50 megawatts. Now they're multiple gigawatts. There used to be excess capacity in the grid. Essentially, the utilities in the grid were giving free option value to people who had to interconnect load on a short time scale. That is no longer the case. We have sucked up all of the spare capacity and optionality in the grid. The hyperscalers need to step up and make longer term investments if they're going to ensure they're going to have the gigawatts of power that they need to keep growing their businesses and to keep supporting our economy. I think that's important. That's I think maybe it's more of an industrial policy shift that I want to see happen in the private markets, is longer term commitment to energy sources that fill the long-term strategic needs of those hyperscalers, because they need to think longer term than they're used to thinking. Because the reality is they're going to keep needing a lot of power for whatever new LLMs we invent going forward.
But generally, it sounds like you're relatively optimistic that the nuclear market at the moment seems to have the support that it needs. There's fresh breath being blown in from the hyperscalers. It's perhaps just a matter of innovation, like what Blue Energy is doing, or getting hyperscalers to maybe quantify how much demand they think they're going to need for the data centers. It's difficult to know that utilization measure, but I think with a matter of time, it could be possible to have that clarity and move all technologies forward. You seem pretty optimistic.
I am optimistic. I think as a founder, I'm perhaps self-selected to be optimistic. Otherwise, I wouldn't be a founder. I am optimistic. I think this will work. You have to have high conviction to do something like this. And we and the team at Blue Energy have high conviction that this will work. This is the surest path to getting nuclear project financeable. We've never had a better macroeconomic or policy environment to execute on it. And we've never had one that is more durable. Even with the amount of uncertainty in markets today, there is, I think you can point to, there's long-term, durable, strategic rationale for why to invest in new nuclear that can be project financed in the long run today.
Yeah, an innovation based on, 75 years of technology that we've had commercially available, 75 years of technology that couldn't be project financed. So there's a way up.
That's right. Yeah, we stand on the shoulders of giants. No one should question whether nuclear power will work. It works.
It's proven.
We shouldn't look at it as it's weird. It's like this technology we inherited from a previous civilization. It's like, what are all these nuclear power plants? We kind of stumbled upon them. They're like, they were here when the mountains were here. I was like, we completely forgot how they were built. It's like, no, guys, we built these things. We can build them again, but let's use modern, automated manufacturing, robotic welding processes to get it done in a way that we know how to finance new power infrastructure.
Brilliant. Well, thank you very much for joining us on the podcast today, Jake. Maybe, we'll have you back in a year so you can give us an update on how robots are working in the prefab yards. And it would be nice to hear it come true.
I would love that. Thank you, Bridget.
Yeah, thank you for listening, listeners. And you can find the Interchange Recharged wherever you get your podcasts. Get you next time.